right? When things are said very clearly and correctly with less justification, um, that's often enough. Okay. Um, so, any other questions on assignment number 3? So that was number 6. So let's go on and do some more examples. We'll get some more practice in there, and please do those examples that I'm doing, because that's the practice that you need to do. So I do the example, and then you should repeat it on your own to get the practice that you need. And then, of course, you have a solution when you're done doing it on your own. All right, so we left off on a certain example here. Right. So let A, B, C be sets, and you want to prove the following statement is true. If A intersection C is the empty set, then B minus A union C is equal to B union C minus A. And before we get into the proof, I want you to note the following. It isn't true that these are equal in general. I'm saying if A is a subset of C, if A intersection C is the empty set, then this is true. When this is true, that's true. Okay? Not that this is true in general. It certainly isn't. It isn't the case that B minus A union C is B union C minus A. For example, if A is 1, 2, B is 1, 3, and C is 2, 3, notice that A intersection C is not the empty set. And then if you work out what these two sets are, well, B minus A is just the element 3. Union C is 3, union 2, 3 is 2, 3. B union C is 1, 2, 3, minus A, which is 1, 2, is just the element 3. So as you can see, they're not the same. Okay, but in the case that A and C do not intersect in the empty set, it is. Okay. 3 strategies for proving an implication. We're just going to do a direct proof. Okay? So assume that A intersection C is empty. Prove that this is the case. We have several strategies for proving that two sets are equal. Right, there was those set identities, De Morgan's law, and distribution, and all that jazz. I thought maybe this example would work that way, but it didn't. It doesn't quite work out that way. So we're just going to do it the more laborious way, which is to show that B minus A union C is a subset of B union C minus A. And the other way around, B union C minus A is a subset of this. Okay, so direct proof. And here we tip off the reader, this is a direct proof. Assume that A intersection C is equal to the empty set. So we're making that assumption, and that assumption will be used throughout this proof. Okay. Let X be an element of this. So now what we want to do is show that X is an element of this, which will show that this set is a subset of this set. So let X be an element of B minus A union C. So now we go straight to the definition. This means that X is in B minus A, or X is in C. If X is in B minus A, so this is an or. Either X is here or X is here. So when you have this or situation, right, it means one is true and the other is false, or one is true and one is false and the other is true, or they're both true. Okay, but you don't know which. So all you can do is take them one by one. Well, okay, let's take the first one. Assume that x is an element of b minus a. If x is an element of b minus a, then by definition, x is in b and x is not in a. Okay, here, pay attention to this. Because x is in b, x is in b union c. Right? X is in b, which means that x is in b union anything. Okay, it doesn't matter what that anything is. Because x is in b, x is in b union anything. So which anything am I interested in? I'm interested in b union c. So because x is in b, x is in b union c. Therefore, x is in b union c, and x is not in a. And that's the two pieces of information that we need to show that x is in b union c minus a. Right? To be in b union c minus a, we got to be in b union c, and we got to not be in a. And we have both of those. So there it is. All right. So that's if x is in b minus a. Now we're going to look at if x is in c. If x is in c, now we got to show that x is in b union c minus a. If x is in c, then because a intersection c is equal to empty set, what? A and c have nothing in their intersection. If x is in c, then because a and c don't overlap, what? Where is x not?
In A.
Is not in A. And that's an important bit of information because, right, we want to show it's in B union C minus A, that x.
Right.
So yeah, so that it's not in A is an important point. All right. Again, also because x is in C, right, doing the same trick as before, x is in B union C. It's in C union anything. Which anything am I interested in? I'm interested in B. So I got that x is in B union C, and I got that x is not in A. So what? So what?
X is in B union C minus A.
Exactly. Therefore, and we're done. Right? We let x be in B minus A union C, which gave us two cases, case 1 and case 2. In case 1, x was in B union C minus A. In case 2, that was case 1, we got that x is in B union C minus A. In case 2, we got that x is in B union C minus A. So there it is. We let x be in the first set, and the x was in the second set. There was two possibilities to consider, but in each possibility we won out. All right, so now what else do we have to do to show that this set is equal to this set? What's the next thing to show?
B union C minus A is a subset of B minus A union C.
Mm-hmm. So now we want to show that B union C minus A is a subset of B minus A union C. First sentence. First sentence of this part.
Let X be an element of B union C minus A.
Now we have to show that it's in B minus A union C. Okay? So, by definition, what? This means that X is in this set. This means what? That means that X is an element of what? And X is not an element of what?
X is an element of B union C. X is not an element of A.
Right, and X is not an element of A. Well, X being in B union C means X is in B or X is in C. Right? Therefore, X is in B and not in A, or what? X is in X is in B union C, meaning X is in B or X is in C. And also, X is not in A in either case. So there's two cases again, because you got this union thing, right? That means X is in B, and in that case, X is not in A as well. Or what?
X is in C.
And
not in A.
Yeah, X is not in A. Right? Well, if X is in B and X is not in A, then X is an element of what set? What does this mean exactly? If you're in B but not in A, then where are you? By definition.
In B minus A.
Yeah, then you're in B minus A. In the second case, if X isn't, or no, then you're in B minus A. Then X is an element. Well, again, with this union business, if you're in one set, then you're in the union of that set with anything else. Right? Then X is an element. Oops. X is an element of B minus A union C. Right? If you're in one set, then you're in that set union whatever other set you'd like. Because it's an OR statement. Right? This means X is in B minus A, or X is in some other bizarre location. But the bizarre location is irrelevant because we already know that X is in B minus A. It's an OR statement. Well, if, in the second case, if X is in C and X is not in A, then, again, X is an element of B minus A union C. Because it's in C. It doesn't matter if it's in the other thing. And that's that. Oops. All right. So notice the sort of overall structure of the proof here. We're trying to prove this statement here. We're trying to prove this. If A intersection C is the empty set, then B minus A union C is equal to B union C minus A. So we are doing a direct proof. We assume that this is the case. And then we show that the first set is a subset of the second. And then we show that the second is a subset of the first. So on assignment 3, number 4. Number 4. This is the way the proof for this one should look. Here is the template. So on assignment 3, number 4, so we're asked to prove that if A intersection C is a subset of B, and A intersection B is a subset of C, then A intersection C is equal to B intersection C. Okay, so you're going to want to do a direct proof in this case. You're going to want to do a direct proof. So here is a template of what your proof should look like. Proof. All right. Assume that A intersection C is a subset of B, and A intersection B is a subset of C. Right? And now you're going to want to show that A intersection C is a subset of B intersection C. Right? So you're going to let X be an element of A intersection C, blah, 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 blah. Therefore, X is an element of B intersection C, period. And then you're going to want to show that B intersection C is a subset of A intersection C. It's essentially going to be the same thing. Let X be an element of A intersection C, blah, 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 blah. Therefore, X is an element of, B intersection C, A intersection C. It's going to be the same proof, just switching A and B around. So if you wanted to say that this proof is the same as that, just with A and B exchanged, that would be okay. But this is a basic template for how your proof should look like. So all you got to do is fill in the blah, blah, blah. Okay, just fill in those dots. Fill in the blank. I mean, there's going to, be some things that need saying in that case, but, right?
I think I see a mistake.
Mm-hmm.
So if A intersection B, so as soon as A intersection C is a subset of B, and B intersection C is a subset of A.
Alright, do I have the A's and B's off? Hold on. If A intersection C, B intersection C is a subset of A, do I have A intersection? Sorry, I didn't write it down right. A intersection C is a subset of B, and B intersection C is a subset of A. A intersection C is in B. B intersection C is in A. So C is the both intersections. Excuse me. And then you want to show that A intersection C is equal to B intersection C. And this is right. Okay? So give that a go and let me know if you've got any questions. And maybe you need another hint to get that one moving. All right. Let's talk a little bit about if and only if type statements. Oh, let's try one more. I have one more example of this I would like to do. So here's another example. Of proving an implication. So prove that if A intersection B is equal to the empty set, then A intersection B complement is equal to B complement. All right, if A intersection B is the empty set, then A intersection B complement is equal to B complement. Or A intersection, A union B complement is equal to B complement. The intersection would be equal to A. Okay, so let's give a proof of this statement. Let's start with the direct proof. Let's start with the direct proof. So in the direct proof of the if-then statement, what's the first sentence?
Assume that A intersection B equals the empty set.
Assume that A intersection B is equal to the empty set. And now we want to show that A union B complement is equal to B complement. So we want to show that this is a subset of this. A union B complement is a subset of B complement. And that B complement is a subset of A union B complement. Well, one of those is easy. Right? It is true that Right? B complement is a subset of A union B complement. How? Why is B complement a subset of A union B complement? What's the reason for that? Right? What is union? What is the union of two sets? Right? A union B, that's the set of all. Let's just write it down here even. It's not bad to write it down. It's the set of all X such that X is in A
or
X is in B complement. So why is it true that B must be a subset of that? It's the set of all X's that are in A or in B. B complement, sorry. It's true just by definition. It's true just by definition of or. I mean, we could do it more formally. I mean, maybe it's not quite hitting home that it's just true by definition, but you know, let's just write it out. All right, so we assume that A intersection B is the empty set. Right, now we want to show that B complement is a subset of A union B complement and the other way around. So for this part, let me just write it down here. We start by saying let X be an element of B complement. Right, therefore, X is an element of A union B complement, just by definition. Just by definition. I mean, so you could just say it's true by definition. Right, because this is everything that's in B complement or the other thing. So when you have stuff that's in B complement, it's in the union of the two. All right, the other way around is a little more involved, a little more entertainment value. Let X be an element of A union B complement. So now we got to show that X is an element of B complement. Right? Well, by definition, right, because X is an A union B complement, right, that means that X is in where or X is in where?
A or B complement.
Right, A or B complement. Right. The second case is our desired outcome. Right, so now you have to consider both cases. That's the first case and that's the second case. Right, either X is in A or X is in B complement. Right, the second case is what we want, that it's in B complement. Right? We're trying to show that X is in B complement. So the second case is the desired outcome. So in the first case, right, if X is an element of A, then because, what's our assumption throughout this whole proof? What's the overarching assumption in this direct proof?
A intersection B is the empty set.
A intersection B is equal to the empty set. Because A intersection B is the empty set and X is in A, we get what? X is in A, and A and B don't overlap. So where is X not? All right, here's A, here's B. Oops. There's no overlap between A and B. X is inside of A. So where is X not?
In B.
Yeah, X is not in B. X is not in B. That is, in other words, X is where?
In B not.
In B complement, yeah. As required. If you like the as required thing. End of proof. All right. So, for practice, for next time, okay, let's do the following. For next time, you prove that if A intersection or A union, let's do it this way. If A intersection B is equal to the empty set, then A intersection B complement is A. So you prove this next time on your own. Okay, then we'll go over that next time. All right, give that one a shot. All right, let's talk a little bit about if and only if type statements. So proving logical equivalences or double implications. So recall that P, if and only if Q is logically equivalent to P implies Q and Q implies P. Right? A double implication, a logical equivalence is also known as a double implication. Right? P, if and only if Q, means P implies Q, and Q implies P. So, when you're trying to prove a logical equivalence, you can do it via a string of logical equivalences, like we have done in the first assignment. Right? We had those tautological equivalences, and we made other tautological equivalences using those known tautologies, De Morgan's law, exportation, distribution, idempotent, all those things. Okay? So you can do it via a chain of logical equivalences, although that's not always possible. In which case, you would do it by proving the double implication. Right? So a proof that P, if and only if Q is true, could either be 1, a chain of logical equivalences could be either, or 2, a proof that P implies Q, and a proof that Q implies P. So 2 implication proofs. The implication one way, the implication the other way. P implies Q and Q implies P. It's kind of like proving that, P is a subset of Q and Q is a subset of P when you're talking about subsets, right? Because subset is defined with implication. I mean, these are all sort of like 2 faces of the same thing, right? If P and Q are sets, then P is equal to Q if and only if P is a subset of Q and Q is a subset of P. When P and Q are propositions, P is logically equivalent to Q if and only if P implies Q and Q implies P. But as we've been talking about since the beginning of the semester, implications are really like containment relationships. So it's the structure, templates of such proofs are pretty much, they look the same. Now, when you're doing a proof that P implies Q or Q implies P, and a proof that Q implies P, right? You have 3 strategies for each. You can do direct proof, or proof by contrapositive, or proof by contradiction. You can do any one of the 3 on each one. Right? You don't have to do both direct proofs. You can do one proof direct, one by contrapositive. That's the way I often like to do it. You prove that P implies Q, and then you prove that P naught implies Q naught. If you got P, then you got to have Q. If you don't have P, then you don't have Q. So that's one way to do it. Like that's direct proof, and that's contrapositive. Or you could do a direct proof and contradiction, or both by contradiction, or both by contrapositive. Whatever seems appropriate. So let's take a look at an example of that. So prove the following. It's true. That A is a subset of B if and only if A union B is equal to B. Prove that A is a subset of B if and only if A union B is equal to B. Okay, so the proof will look this way, and this is one way it's often written. So there's going to be 2 proofs, an implication proof in one direction, and then the implication proof in the other direction. So I think we'll do them both direct proof. So assume that A is a subset of B, and then we'll argue that A union B is equal to B. And then the proof the other way, assume that A union B is equal to B, and then we'll prove that A is a subset of B. Okay, but we've only got 1 minute left, so there's not enough time to do it. So we'll go over that next time, right? But when you're trying to prove an if and only if statement, typically you're going to have to do 2 proofs. You have to do the implication in one direction and the implication in the other direction. That A subset of B implies A union B equals B, and that A union B equals B implies A is a subset of B. Okay? Alrighty, so that's all for today. So we'll see you on Wednesday. Please get started on the assignment. Work through some of these examples on your own, and then we'll talk next time. If you need extra help, okay, we can set up a time. If you want to do some proofs and I will watch you do the proof and help you through it, we can do that too. All right, that's often effective. If you're up for that sort of thing, it's effective, but it's kind of intense for some people. All right, but if you want to do that, we can do that. You'll aim your camera at the paper, you start writing, and I'll watch you write, and help you to form that proof. Okay, so let me know if you need some extra time. We can set that up. Alrighty. Okay, everybody, have a good day.